I have mentioned that functions have interesting properties, and that these can be most easily recognized by sketching the function in graph form. There are some things about a function that we automatically regard as interesting. You may be familiar with our interest in x and y intercepts, limiting values, or even singularities of a function. Another feature that we are always particularly interested in are a function's stationary points. A stationary point is when the rate of change of the function is zero. On a graph, this means that at stationary points the gradient is zero, and so the tangent to the curve at these points will be flat lines horizontal to the x-axis. On this graph here we identify 4 such stationary points, and we notice that all of them are slightly different. The first thing to note is that at all these points, the gradient is zero, and that's what defines them as stationary points. Point A lies at the top of a hill, which is characterized by the fact that the gradient is positive before the point and then negative after it. We call this type of stationary point a local maxima. It won't be a surprise that point C is an example of what we call a local minima, since it is at the bottom of a valley, with the gradient changing from negative before the point to positive after it. Points B and D don't lie at local maxima or minima, but are nonetheless stationary points since their gradient is zero. We classify these types of stationary points as points of inflection, characterized by the fact that the gradient goes from negative to zero to negative again, or from positive to zero to positive again. The next question is, how do we go about finding the stationary points of a function? Here is where we use differentiation. We know that when we differentiate a function y, we get a new function, dy dx, which tells us the gradient of the original function at any point. Since we are interested in the points where the gradient is zero, we state that at stationary points, dy dx must equal zero. From this we can solve the equation to see what x values satisfy, and these will be the x-coordinates of the stationary points. We find dy dx, we set it to zero, and then we solve the equation to find the x-coordinates. Once we have the x-coordinates, we can easily find the y-coordinate by subbing the x value back into the original function. For example, to find the stationary points of y is equal to 3x cubed minus 9x, we first differentiate to get dy dx, which comes out as 9x squared minus 9. We then set this to 0 and solve the equation for x. When we solve this, we find that x squared must equal 1, and so x must be plus or minus 1. We have therefore calculated that the stationary points must have x-coordinates of plus and minus 1. We now sub these into the original function to find the y-coordinates. At x is equal to negative 1, y is just equal to 3 lots of negative 1 cubed minus 9 times negative 1, which comes out as 6. At x equals 1, we sub 1 in and we get the result of minus 6. The stationary points are therefore at negative 1, 6 and 1, negative 6. You might want to note that you're not always asked to find the y-coordinates of the stationary points. You might then be asked to classify these stationary points, which means to deduce whether they are local maxima, local minima, or points of inflection. I will first state how to do this and then explain why it is the case. The way to classify stationary points is to take the dy dx function that you'd already calculated and differentiate it again. We denote this new function as d2y over dx squared. We then take the x-coordinate of the stationary point that we care about and we input it into this second derivative function. When we calculate the result, we don't really care about the number we get out, just whether it is positive, negative, or 0. If the result is negative, the stationary point is a local maxima. If the result is positive, then the stationary point is a local minima, and if it is 0, it is a point of inflection. To understand this, remember that when we differentiate dy dx to get to d2y over dx squared, we are asking what is the rate of change of dy dx? In other words, what is the rate of change of the gradient? We have seen that at maximum points, the gradient goes from positive to 0 to negative, and so the gradient is clearly decreasing at these points, hence the negative d2y over dx squared. Likewise, at local minima, the gradient is increasing from negative to 0 to positive. Points of inflection are interesting because not only is the gradient 0, but so is the rate of change of the gradient. Using our previous example, we differentiate dy dx to get d2y over dx squared is equal to 18x. When we sub x equals minus 1 into this, we get negative 18, and so we deduce that the stationary point at x equals minus 1 must be a local maxima. When we sub x equals 1, we get d2y over dx squared equals 18, which is positive, showing us that this stationary point is a local minima.